We ended the last panel on the note of sine theta t being greater than 1 when our incident angle is supercritical, meaning it's greater than the critical angle. So in the case of light going from glass to air, if we're more than 41, 42 degrees, we're supercritical. In that case, we have this very strange result, which does not coincide with what we normally think about the sine function going from 0 to 1, then back to 0, then minus 1, and then back to 0. So how can this be? Well, we write sine theta t using the Euler relation, and we can have sine theta t is e to the j theta t minus e to the minus j theta t over 2j, and that's just direct algebra. Now, let's see what happens if we make the angle complex. Making the angle a complex number does not coincide with our common knowledge of angles, because normally we think of angles going from 0 to 2 pi. What happens if we make the angle complex? So alpha plus j beta. So what we do is we take that and we substitute into here and do the algebra. The sine of the complex angle theta t by substitution is just putting in for theta t alpha plus j beta, and then using the properties of exponents to multiply everything out. So this term, j times j minus 1, e to the minus beta, e to the j alpha. So this thing is okay, it's not doing anything funny. E to the j alpha has a magnitude of 1, and this, if beta is positive, is going to decay away. But look at the second term. Here we have e to the minus j alpha again, but we have minus j times j, which is plus beta. This term grows. So depending on beta, we can find a beta for which this whole term is greater than 1. And that's the meaning, algebraically, of a complex angle. To actually visualize it geometrically, there's no direct way to do it, but it has an implication in wave dynamics, which we'll see in the following panels. Finally, since we now have a better feeling for why sine of theta t is greater than 1 when the incident angle is supercritical, when we compute cosine of theta t, we see that since sine is greater than 1 in this case, this number is purely imaginary and there's 2 possible roots. To actually get a feeling for the complex angle, we have to see the effects of that in dynamics. So we'll apply this geometry and this algebra to the form of our electrical wave, our magnetic wave, leaving the boundary, and then we will see exactly what the physical implications are. We have at our disposal knowledge about the angles from the previous panels. Now we need to apply it to dynamics. We're shooting in the medium 1, and normally this is going to be glass, and this is air. So we're going from slow to fast. We're focusing on the transmitted wave, so K2 has a magnitude, K2 equal to omega square root mu 2 epsilon 2. We're in air, so mu 2 is mu 0. Now, what's important, of course, is to calculate the electric and magnetic fields. So let's take the case where the movement of the electric field is in and out of the board. That's the first case that we did in class. That's the transverse electric vibration or polarization in and out of the board. So here we are. The direction is in the j direction into the board. That's the direction of vibration. Now we have the amplitude. The amplitude is scalar. It could be complex, but it's a scalar number EYT. EYT is tau, the transmission coefficient, times the incident amplitude, as we saw previously. Direction of vibration, amplitude, and the phase. The phase is e to the minus j phi, and phi is this classic expression here that we've seen a number of times before. What's different is we're supercritical. That means this number is bigger than 1. And this number, cos theta t, is plus or minus ja, purely imaginary. Now, which sign to pick? Well, this is in the exponential, so it's multiplied by minus j. Therefore, we must have the minus sign. If we pick the plus sign, when we exponentiate this here, we're going to get minus j times plus j, which is 1, which means as we increase x, the wave is getting larger, which is physically nonsensical. So we must pick the minus sign here. When we pick the minus sign and we put that in for phi up here, we can see that we get a combination of a negatively decaying exponential times an oscillating piece. And we're going to look at that algebra in a little more detail in the next panel. After that, when we get the final form for E, we'll compute H. After we get H, we'll compute the energy transferred away from the interface in the x direction.